my gosh.
Yes. Well, she's not here anymore.
Oh, she's gone.
She came in just
I have to do it again.
Yeah, I saw her
Every
scurry out real fast.
Every day.
Yeah,
Yeah, her boyfriend came to pick her
and
up.
it's filled with liquid nitrogen
And she
twice a
took
day.
too long. So
What's
he
today's
said
date?
goodbye to everybody. He got mad.
Thank you.
I had 5 years to say goodbye.
So, I thought we would take a little bit of a departure today, and what happened? Oh.
That happened.
And talk about kind of basic mechanisms of chemical catalysis. And so, kind of like so far, we've done mostly kinetics, and we haven't paid any attention really to the enzyme itself. We've mostly done, in fact, mathematics, and we almost completely ignored what the enzyme looks like, other than we kind of drew an enzyme that looks like this, a Pac-Man for the enzyme. And in some ways, that's like the crudest version you can have, but and then we drew kind of like the substrate like this, and maybe this is how enzymes looked like around the year 1930 or something like that. And then it kind of goes in. This is sometimes called a lock and key, and it fits in there to make the Michaelis complex. And then ultimately that goes on to make products. We did all sorts of things so far. Most recently, we looked at a lot of the other species that are along the reaction pathway, like EP and E plus P, and we saw how to treat this with kinetic shortcuts. What else did we do? We did looked at K-cat over Km conditions, competition of various substrates, etc. So instead, so Erica and Jamie have both been doing kinetic simulations, and we're going to do that. Maybe they'll lead the class. We're going to do that maybe next time using Ken Johnson's software. And Scott and I were talking about this, and it goes all the way back to original programs written by Carl Friedman with Freeman. Carl Frieden, where they use numerical integration to simulate kinetics, and there's some great programs to do that, which don't require a whole lot of math, and they give you a lot of intuition. But we thought about doing that today, but yeah, it was great. His talk was great. Yeah. Okay.
Is it Riker?
So anyhow, there are a lot of people. So I never met Bill Jenks, and so I always he's one of these sort of almost mythical figures in science, and I'm going to talk about it probably maybe this week and next week. I don't know. It depends on at least a couple of weeks. I never met him, but I always ask people to tell me stories about him, and so Dan Hirschlag's told me many stories about him. So anyhow, so when you think about how enzymes work, so what do you guys think is the most? Who is it? Richard?
We're trying to place a face to the
Yep,
name.
that's him. You could look up Bill Jenks to get a picture of him. All the pictures I've ever seen of Bill Jenks where he wears very thick black glasses. So what's the most obvious way that enzymes could work?
Acid base.
So I'm going to write down a quote from Jenks. The most obvious means, let me make this a little smaller. Sorry about the flashing. I don't know how to fix that. By which an enzyme might increase the rate of a bimolecular reaction. Let's go with that. By which an enzyme that's a big clue. So you know, sometimes a lot of when we're practicing talks and things like that, I always encourage you guys to say the obvious. So sometimes you have to state the obvious. So the most obvious means by which an enzyme might increase the rate of a bimolecular reaction is simply to do what?
Bring them closer together.
Yes, yes. Bring the reacting molecules together. And I'm copying this verbatim. Bring the reacting molecules together at the active site of an enzyme. Okay, so that's chapter 1, paragraph 1. And that's what he says. The most obvious means by which an enzyme might increase the rate of a bimolecular reaction is simply to bring the reacting molecules together at the active site of the enzyme. And so we'll talk about that. And he calls this mechanism right here approximation. So it's sort of an old-fashioned use of that word, but it means to bring two things close together in approximation. So then I won't write any more down, but he says the two most important questions with respect to this topic are, first, the magnitude of the rate enhancement, which might be expected from such an approximation of the reactants, and second, the mechanism by which this rate enhancement is brought about. And so the first question is best approached by examining rate accelerations that are brought about when reactants are brought together in model systems, either by being covalently linked in the same molecule or by some weak and reversible binding force, like a coacervate maybe. And there's no very complete answer to the second question at the present time, but it's possible to reach some tentative conclusions about the factors, and they have to do with entropy. So it's kind of fun to do this, and I thought, you know, probably this is all we'll do today, because then you can get into things like Erica said about acid-base chemistry and so on, which are more subtle and have to do with sort of physical organic chemistry, but this just has to do with bringing two things close together. And so I'm just going to write out a mechanism and how to do this. And so the first reaction is it's acyl trans. Which one should I pick? Let's do. I guess they're actually all very similar. They're acyl transfer reactions. And so it's all model system stuff. And what you do is you compare the rate of a unimolecular reaction to a bimolecular reaction. Okay, so we've got like undergraduates here who know more organic chemistry than probably us who haven't looked at it for a long time have. So, like Dan, I'll pick on you, and Sarah, you're here, and Ananya. You guys all just took organic, right? Yeah. Because you're like rising juniors, so, all right. So let's start with this thing. And so the question is, what's the reaction that's going to happen? Well, you know, I actually have the reaction in front of me, so that makes it easier for me. But This is going to react. And Dan, what do you think the reaction products are going to be? This looks like something that Funk would give you, right? Or is it easier than that?
Ortho.
What do you think's the nucleophile? If I write this over as right, this guy's going to attack here, and then this is going to leave. And this is a really good paranitrophenol is a really good leaving group, or phenolate. Remember the pK is around 7, so that's why they have it set up like that. So you're going to get an acid anhydride of this thing. So we can write down. So one product's going to be paranitro phenolate. Depending on the pH, that might be protonated too. I know that has a pKa around 7. So it's a really good leaving group. So as opposed to, if you didn't have the paranitro, if you just had phenol, do you remember the pKa on phenol? It's like 10. So phenol doesn't want to leave as a minus because it really needs to be protonated. You need general acid chemistry. But paranitrophenol is happy to leave as the anion. Because you can delocalize that minus charge out onto the nitro through doing things like this. Sorry, undo. Doing things like and then pushing that out there to make like a quinones type of thing, right, guys? So anyhow, you don't need to write any of that out. But then the other thing is this anhydride. So it's going to be these two CH2s like that, and then those are going to be each with their own carbonyl. And then this O right there is going to bridge them. And that's an acid anhydride because you could just add water and make a dicarboxylic acid out of that. Okay, so that's one reaction, and that is that a unimolecular or bimolecular reaction? Unimolecular, absolutely. Okay, it's just A goes to B plus C. Okay, so that's a uni. And the rate constant for that, you guys know how to measure that. We talked about that before last time in plotting stuff, and a little bit about that. It's first order decay. Just plot the fraction cleave versus time, and the rate constant for this is pretty good. Oops. It's 0.8 per second. T1 half. We didn't really do this last time, but you probably all know how to do it. T1 half is natural log of 2 over k. So, what's natural log of 2?
1693.
Oh, good, Erica. So what's the half-life, roughly?
Times
0.693 divided by 0.8. It's close enough to 1. About 1 second, right? Get those out of the way. Okay. Alright, so that's a unimolecular. You can look at a bimolecular version of the same reaction. And in the bimolecular reaction, you take acetate. So basically what you do in the bimolecular reaction, let me go ahead and write it down. I'm going to pick a different color ink for this. And so you take acetate, because this is pretty much acetate right there. Okay, and it's going to attack. So you can just take acetate Okay, and you can let it attack that other piece that's up there, but put it in as a methyl group. So I'll take exactly what I have there, but write it with the methyl group. Let me not be lazy. Alright, so we know now that this guy will attack here, and that will leave. So it's going to go to give us the paranitrophenolate again. Which I'll just paste from up above, plus the product of this, okay, which is going to be, we can figure out what that's going to be. This O is going to attack that, and so we're going to end up with something like this. Okay, and so we can write down the rate constant for this. And we'll call this K2. You could use pseudo first order kinetics to do this, like we talked about last time. And so the rate constant on this turns out to be 4 times 10 to the minus 6th inverse molar inverse second. Everybody's okay with those units, right? We did that back 4 weeks ago. Okay. So now, the game that people play is you compare those two rate constants. And when you do that, what people do is they take K1 and divide it by K2. And so you end up with 0.8 per second divided by 4 times 10 to the minus 6th per second per molar. And that's equal to 2 times 10 to the 5th molar. And so the conclusion is that the effective concentration and that's a new term of carboxylate is 200,000 molar. Okay, so how can we think? Let's see if that makes sense. So K1 is basically equal to well, how do we write? Yeah. I didn't write this out, but the velocity for the first reaction is equal to K1 times the concentration of A, and the velocity for the second reaction is equal to K2 times the concentration of what is essentially A times CO2 minus, because you're bringing that in separately. And if you set them equal to each other, so that they have the same rate, then you end up with K1 times A equals K2 times A times, or so in other words, in order to have those two go at the same rate, the unimolecular and the bimolecular, the exact same pseudo first order rate constant, because if carboxylate is, remember, if carboxylate concentration is super high, then from pseudo first order, you know that product is a pseudo first order rate constant, right, guys? So to get the same pseudo first order rate constant, you would need the carboxylate concentration to be 200,000 molar. So you can think, so that's one of, like, Jenks is known as one of the great thinkers in enzymology, and it sort of like makes you say, oh wow, that I didn't think about it that way before. So we know we could never put anything into solution at 200,000 molar. But that's what this and there's no enzymes involved here, but when this reaction happens up here, this is effectively present at this would need to be present at 200,000 molar in order to go that fast. So that's kind of the game that they play. So the rest of the examples that I have here are pretty similar. I don't know if you want to write out another one or not. But probably not. But there is another example. These are all from First's enzymology. But there's another example, and I won't write it out, but it's acyl transfer in aspirin. And there, the effective concentration of CO2 is even bigger. It's 2 times 10 to the 7th. $20 million molar. What do you think, Josh?
When you say the effective concentration is 2 times 10 to the 7th molar, like in relation to what? So like in the last example, that was like in relation to...
In relation...
electrophile, right? Like our carbonyl.
Yeah, so let's look at the last example, because they're all the same. So in this example, that means that in order for this reaction to go at the same rate as this reaction, this would have to be present at 200,000 molar. So that means that in this reaction, the unimolecular reaction, this is present at an effective concentration of 200,000 molar.
Right.
So it's not the actual concentration.
Right.
This rate is actually independent of concentration. It would go at a half-life of 1 second whether this was, you had a 1 millimolar solution of this or a 1 molar or a 1 nanomolar solution, it would still have that same rate. But that's how, because, and so why does this go so fast is because it's present locally. And so part of reaction, transition state theory and reaction theory has to do with collisions, frequency of collisions and orientation of collisions. And so this can collide really frequently because it's attached.
Yeah. I was just thinking, so like in this case, it's got an effective concentration because it's so close to the electrophile.
Yeah.
But then in aspirin, what is the carboxylate close to that we're
Well,
attacking?
Well, we can do the aspirin example. Let's do it. So, in this example, it's hang on 1 second, because I didn't look at this. Okay. It's yeah, it's this. Okay, so, and you actually can make sense. I think we can make sense out of this. So this is the reaction, and we can kind of predict now. Maybe after looking at those last ones, let's actually just, instead of, let's write this out. I like to write it out this way. L minus, okay. So we know this is going to attack down here to do that, and then this is going to leave, right? And so these guys are ortho to one another in this reaction. And we can go ahead, I'm sure you can go ahead and write out the products. Like that. And this rate constant is what they give in the book, is greater than or equal to 0.02 per second. It's kind of neat, right, how the units work, and they give you back molar when you divide a K1 time by a K2. I think I'm going to put this on another, I should be able to put this on another board. Yeah. Let's just put it here. So I think the art of doing these sorts of things is to pick what's a good model for a bimolecular reaction. And so what these guys did is they split this guy up into two pieces. Okay, so piece one is that. So we'll go ahead and write that down here. And, you know, I bet if we got Funk and Feldman in here, they'd have some arguments about whether this is right or not. But that's piece one. And then piece... Yeah.
Are we assuming that the unimolecular, are we, like, considering that the enzyme catalyzed reaction?
Yeah.
Is that the, okay.
Yeah.
And then calculating the rate constant and then assuming...
Yeah. This is what an enzyme does. Yeah. So we can take that one, and then, so that's sort of a aromatic... What would you guys call that thing? It's an ester, right?
Mm-hmm.
Is that an aromatic ester? And then, yeah, and then this is an aromatic acid. So then they take this as the other piece. Okay, and they ignore that thing on the top. that CO2H on the top that I didn't circle. Okay, it's not, I don't know whether that's important or not. But for whatever reason, they don't include that. So then they make this piece. And they let these two guys react. And so it's the same reaction. This guy's going to come over here and attack there and leave like that. Okay? And they're going to make, you kind of know what they're going to make. You can write it out now. But I'll write it out. So they're going to make, the left guy's going to look like this. Oh, it's just gonna be a phenolate, and then the right guy is gonna look like this. And then he's gonna pick up the remaining part. I need to make this smaller. I didn't plan very well. Ah! Alright, I'll get this right. There you go. And it turns out this rate's super slow, because you know it has to be, because you know the answer is going to be bigger, and even the unimolecular was somewhat smaller. So this has got to be really, really slow. So in fact, K2 for this is about 10 to the minus 10th is what they give. Probably because it's so slow they have a hard time measuring it accurately. And so now you can do the math on K1 over K2. And it's equal to what I said, 2 times 10 to the 7th. Greater than or equal to molar. So why is this one have an even higher effective concentration than the other one does? Yeah, I don't know.
You have no withdrawn group on the electrophile, so it's not going to lower the lumen, so it's not going to make it go as fast.
You mean missing this group up here?
Yeah.
Yeah,
The other one you have
that's
a nitro
cheating
group.
in some ways, because that has nothing to do with effective concentrations. I'm just copying what's out of the textbook. So
I think also here, the sterics favor
Yeah.
the right orientation for the attack.
Yeah.
In the previous one, you had a lot of rotatable groups between the two.
yeah, that's really true. So next time, and I didn't prepare, so I don't want to hack this up. But it all has to do with what Scott's talking about, like orientation, and Jenks dissects it all into like translational. It gets interesting because it gets into physical chemistry, entropy of translation, rotation, vibration, and breaking it all out into pieces and showing that you can understand all this in terms of entropy terms from transition state theory. But the bottom line is that what an enzyme is doing is it's bringing the two pieces together, just like in the bimolecular reaction. And moreover, it's probably orienting them properly. And so ignoring proton transfer, quantum mechanics, tunneling, acid-base chemistry, just the very process of bringing them into thousands to millions of molar effective concentrations in the right orientation, that's a major way that enzymes work. Okay, that's all I got for today. Unless you want to talk about acid-base chemistry. It's up to you guys. I could do a really quick thing on general acid-base chemistry. All right, we'll do general acid. So that's the most obvious way that enzymes work, and what Jenks says, and I believe him. Okay, I believe that that's true. So another way that enzymes work is by general acid-base chemistry. And so what you can do is first look at the uncatalyzed transition state. TS for transition state. And so a lot of enzymologists will compare an uncatalyzed reaction to a catalyzed reaction. Some theoreticians will too. They'll do calculations, quantum mechanics on an uncatalyzed transition state. And so, so one reaction is uncatalyzed attack of water, hydrolysis of an ester. So if you draw just a general ester, and you let water attack it, what two products do we get?
Alcohol.
An alcohol and an acid, right? Yeah. But it goes through a transition state first, and so you can try to draw out the transition state, and guess what that's going to look like. And so let me go back and erase this, because this actually happens in steps, right? So the first thing it does is it makes the, what do they call that, the tetrahedral anion?
Intermediate.
Tetrahedral intermediate, yeah. And so when it does that, in the process of doing that, the way the book has it is somewhere along the way, before it's gone totally single bond, but it's halfway between double and single, you can draw it like that. Instead of being fully anionic, it's like partially anionic. And the water has partial bond formation there, so it develops charge. Has to stay neutral, so if there's delta minus, there must be a delta plus somewhere else, and it's on that oxygen, right? Does that make sense? And so that's the uncatalyzed transition state there. And so the way this is often taught is it says, you know, the uncatalyzed attack of water on an ester leads to a transition state in which a positive charge develops on the attacking water molecule and a negative charge on the carbonyl oxygen. And so that's one way of looking at the reaction. And so you can say, well, you know, which is worse, a partial minus charge on a carbonyl or a partial positive charge on water? What do you think is worse? Which is more unfavorable?
Partial positive on water.
Yeah, it's a partial positive on water. This is really bad news. Okay. Because that oxygen normally is partial minus, right, in water. It's polar covalent, and when you do the bond polarity, we know the bonds are like this, and so it's usually partial minus, and up here it's already partial minus. So this isn't so unhappy, but this is really unhappy. And so what enzymes do is they fix that. They remove that delta minus and take it off of that oxygen. And so so general bases can do that. So we could take the same reaction and paste it there and ask, well, if we bring in a base, and what's the definition of a Bronsted base? A proton acceptor, proton acceptor. So we need something to accept that proton. And in proteins, what might you pick? It needs to be in a functional form. So the functional form of a Bronsted base means it has to be deprotonated. in order to pick up the proton. So something with a pKa around neutrality, because it needs to be fairly basic. If you took something that was really basic, like say lysine, that's a really good base. It would love to be really good at pulling that proton, but it's so basic it already has a proton, right? Lysines are arginine, even more. Arginine's always, the basic amino acids are always protonated because they're so basic they pull protons from water. So they're no good. You could take something like an acetate, like glutamate, or aspartate, they have pKs around 4. They're going to be in the functional form, right? They'll be anionic, but they're not very good at accepting protons because that's why they're anionic to start with. And so the compromise is histidine. Histidine has a pK around 7. So it's mostly in the functional form, and it's a decent base. Okay. With that said, this example shows acetate, so I'm going to use acetate, and it's in the functional form almost exclusively. Okay, and what it can do in this transition state I need to shrink this down. I got carried away. Well, we can start to write this transition state over. I'm going to copy it over exactly verbatim, at least the top part. Whoops. But now, this guy's going to go in and attack that hydrogen. It's going to start to pick up that hydrogen, right? So what's going to happen? Well, that hydrogen that's right there that I haven't put any bonds to yet, it's going to be, because this guy's going to become the acid, it's going to become protonated. It's going to pick up that proton. I'm going to have this partially formed and this partially broken, okay? So I'm going to do dot, 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 and dot, dot, dot. So the bond order is going to stay the same on that hydrogen. The bond order is 1 right now. This is really important. You guys got to pay attention because everybody misses. This is pretty subtle. So the bond order on that hydrogen is 1, right? Has 1 bond. It's going to still have 1 bond. We're going to put half here and half there. Because eventually, it's going to be all here. Okay, but in the transition state, we'll draw dot, dot, dot. We'll assume half, but it might not be. It might be fraction, different fraction. So I'm going to put dashed lines on there.
I don't think that's an acetate.
Oh crap, what did I do? Oh, I butchered it. Is that better?
Mm-hmm.
Okay. Thank you, Erica. Okay, so,
Is this actually all happening at once?
in this example it is, yeah.
So you feel confident that the true transition state has
Well, no, but
all
it's
of these like partial.
it's the true there. You can get into. Let's come back to that question in a second. So, but you can basically what happens is now the reason that this oxygen was partial plus up here is its bond order is greater than 2, right? Here the bond order is 2, 1, 2, but here it's 2.5. If you can get it back down to 2, it'll become back to neutral, which will remove this unfavorable charge development on the oxygen. Okay. So this oxygen, its bond order right here is 1 and a half and a half. All right, so let me make that dashed line a little bit better. Like this. So you can see the bond order on that oxygen is back to 2, and so it doesn't have, there is no charge development on it. And instead, what happens is that hold on one second. Well, it just, there's delta minus here. So the total charge, the total partial charge has to add up to the total charge on the reactant side. The reactant side here started out as -1, whereas up above it started neutral. Okay, so -1, you can think of this as -1/2 and -1/2. So charge is still conserved. The total number of bonds is conserved. But now the charge development on that on the oxygen has been removed. There's charge development on this oxygen, but it likes that minus charge because it has it's okay with that because it has a low pKa. And then ultimately, you know what products this will go on to. Okay. So this is the new transition state, and this is an example of general base catalysis. I didn't write that down. General acid catalysis and they use the word general because there's something called specific acid and specific base catalysis, and so those are already taken, so they use the word general. Specific means it comes from hydronium ion or hydroxide ion, from water itself. Okay, those are what specific means. So if it comes from, generally these come from amino acid side chains, or if you're an RNA person, from a nucleotide, or they could come from buffer, but they don't come from water. Then all of those are considered general acid catalysis. So first write down the uncatalyzed reaction. And so this particular one is hydrolysis of an acetal. So it looks like this. And so the reaction is that this guy goes like that, and then that's eventually going to leave, in this case, as, I guess that would be an alkoxide, not an alcohol, because there's nothing there to protonate it right now. So the transition state that's drawn in first looks like this. This bond is partially broken. Like that. And so the bond order on this oxygen has gone from 2 to 1.5, and so now it's getting negative. And this guy is, you know, if both of the electrons, kind of if you break this bond heterolytically, so that both of the electrons go onto that oxygen, and then this guy here is delta plus, and so that's a transition state for the uncatalyzed reaction. And what's going to happen in the catalyzed reaction is to try to stabilize the development of the negative charge on the leaving group oxygen. And so you bring in a general acid, and so write this reactant over. And so now you can use the same acetate, which you can pretend is a glutamate, but now it needs to be in the other functional form. And because the pKa is typically around 4, but they can be perturbed inside of proteins, pKs are often shifted. So we'll pretend it's shifted up to around neutrality, so you know, some percentages in the protonated form, some percentage in the deprotonated form. This guy is in the protonated form. I call that the functional form of the general acid because it has a proton to donate. And so now, what will happen in the transition state is I'll take and draw this transition state over from up here. But now, this proton is going to begin to transfer. And so it'll be partially broken and partially formed like that. And so as a result, the bond order on the leaving group oxygen here is still 2. Okay? It's still 2. There's one bond there and then half a bond and half a bond. So the charge development on that has been removed. It's no longer delta minus like it was up here. It's now neutral. And instead, that partial charge has been, this is still delta plus, has been moved over to an atom that can better bear that charge. And that oxygen that has a delta minus, this oxygen typically has a pKa, like we said. It could be in the 5 range, but it might be shifted to 7. As opposed to, say, an alkoxide, if that was a primary alcohol, what would its pKa be? 16, 15, yeah. And it has no interest at all in being deprotonated. But this guy's kind of okay with that. So that's general acid catalysis.
Could you argue that that oxygen is donating into the delta plus in your ring?
Yeah,
Wouldn't that be more stable?
Why would it donate in?
because it has an octet. It would be more likely to have the bond between the oxygen in the ring and the carbon that has a delta plus have a second dash line and then have a delta plus on the
Yeah.
oxygen.
Well, if it donates in, then that'll make the bond even harder to break. That's why you would need the general acid catalysis. It won't donate in the lower reaction in here because it can still have the proper bond order of 2 as it leaves. Whereas here, if it's donating in, that will just strengthen the bond and make it harder to break. There's no reason for it to donate in. It can also donate out to here.
Talking about the oxygen, like in the ring structure.
Oh, this one?
Yeah.
Oh, I don't
Punch
know.
the delta
Yeah.
plus.
Yeah. Oh, that may be. That may be. That may be, Dan. In fact, that may be why, in this example, they only worry about fixing this problem. In other words, in the uncatalyzed reaction, there's charge development on 2 different species. There's charge development on the leaving group oxygen, as well as here, delta plus, and we worry all about getting rid of this delta minus. We know it doesn't want to be on an alkoxide with a pK, the leaving group of 15. And this delta plus might not be such bad news because this guy can donate into it. That's why it's more important to fix the other one. So that's 2 ways that enzymes work. This is things that people have been debating for 100 years, how do enzymes work. And there's a lot of thought. There's a whole book here on this whole book is on this. But these are two really interesting things. And to me, one has to. I find the one I really wanted to do was the first one. I find the most interesting is that enzymes simply work by. If someone asks you how do enzymes work, you could say they bring 2 things closer together and they orient them. And that's really true. And how much do you get out of it? Like a lot. And effectively, you can have these fun ideas that are not, you can't do experiments on, where they can increase the concentration by a millionfold, 100,000, a millionfold. And the other way that they work is, which is much more subtle, is that they move protons around. And the way that works is that it takes charge development from atoms that don't like it and moves it over to atoms that don't mind it. But in order for that to happen, the acid or base needs to be in the functional form. And so the bases can't be really basic. You can't use lysine. You can't use arginine as a base because it always has the proton. Okay? And just like nucleic acids, if you're an RNA person, you can't really use the phosphate backbone as an acid or a base. You can't use it as a base because even though it's in the functional form to accept a proton, it's deprotonated. It's a really terrible base. pK is 1. It doesn't want a base. And you can't use it as an acid to donate a proton because it's already donated its proton. Okay? So species that are far removed from neutrality, they're either very low or very high, or lousy acids and bases. And ones that are close to neutrality are decent acids and bases because they have that compromise of being in the functional form and also being an okay acid and base. And if they're near neutrality, then they can be both an acid and a base. They can, like we saw here for acetate, depending on what form it's in. And that leads to this thing called kinetic ambiguity, if you're interested, where you can't tell whether it's an acid or a base. You only know it's one or the other. And it turns out all the kinetics are identical, and you have to do very sort of subtle experiments to try to differentiate this. And we spent many years early in the group's, in our group's research, working on that with C75 and debating whether it was the general acid or the general base in the reaction. And the really just decisive experiment that was finally done that concluded whether it was an acid or base was done by Joe Piccirilli's group. And basically what they did is they took the leaving group and put in a really good leaving group. And like in our case, instead of an alkoxide, they turned it into a thiolate, which is a much better leaving group. The pK is much closer to neutrality. And then they